My break was good. Too short, obviously. It's breaks are always too short, but it was good. I was able to catch up on work a little bit, catch up on sleep a little bit, cook a little bit. So, yeah, always a welcome thing. So, um, now ready to hunker down and for the rest of the semester. How was your break? A little bit. It was a great game. So I watched it with my family actually because my mom went to UCLA too. Although she's always too nervous to watch these big games, and so she was kind of in the other room, like kind of too nervous to watch it. But I was watching it there. But yeah, it's a hell of a game. Just exciting all the way through. I think at first of course I was really sad that UCLA lost, but I mean to lose like that and just to see how well they played. I was proud of them. And also just really excited about what the future is going to be like. So I think kind of that sting of losing is kind of worn off at this point, and now it's just kind of excited about what next year is going to be like. Yeah, Juzang's probably gone. Juzang's probably going to the NBA, but I think most of the others should be back, especially Hawkes. So I think I think they have a really good chance to be really really good next year. Yeah, that buzzer beater was insane. But I mean, they played them tough. I mean, they were expected to lose by like 20. I mean, everyone was saying that there's UCLA has no chance in this game, but like they basically played them basically tied for almost the whole game. So I mean, they played really great. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. Welcome back from the spring break. So how's everyone doing today?
Not too bad. How was your break?
Good, good. Yeah, I was just saying, got to rest a little bit, got to catch up a little bit, got to sleep a little bit. So, got a little bit of everything. Of course, I probably wish, same as probably as you guys, I wish the break was a little bit longer, but, you know, week's all we get. So now it's time to kind of, put our nose down and kind of finish out the semester. So, uh, hopefully you guys had a good restful break too. And I know I was talking to some of you, and I know some professors assigned stuff over the break. So hopefully that wasn't too taxing and you're able to at least catch up on sleep a bit. Okay. So the plan for today is that we're going to continue our lecture notes on free convection, and so we ended at about maybe a third of the way done, and so we should get pretty far today. And so that's most of what I have planned. I did post homework 5, and so homework 5 did go up on Friday. And so that's available for you guys. So you should be able to do everything on homework 5 because that's purely based on internal convection, which is the stuff we worked on before the break. Okay? And I believe the due date for homework 5 is going to be next Monday. Right, so you guys have about a week to work on that. So homework 5 doesn't contain any of the free convection stuff. It's just internal convection. So definitely look back on your notes from before the spring break and from the lecture videos, and you should be good to go. And of course, as always, if you have any questions about the homework or if anything's confusing you, definitely don't be afraid to reach out. I'm always here for you, either through office hours or through email or through Discord. I'm always happy to answer questions. Okay. So any questions on anything before we get started today? Okay, all right, so let's go ahead and get started. And where we left off on was free convection. All right. And so we're on, I think, probably the third major topic in the convection unit. So we've done external convection, we've done internal convection, and now we're on free convection, right? And just to kind of remind you, these are situations where we're not doing anything external to force the flow, right? Because remember, in order to have convection, you always have to have some kind of moving fluid in some way, right? So you have a fluid that's flowing over a surface, and that enhances heat transfer compared to just straight up conduction, right? And so normally when we were doing like our external convection and internal convection, we had something like a pump, we had something like, the atmosphere, the environment, something was forcing the fluid to flow in some way, right? In free convection, we don't have that. And so in free convection, you still have a flow of fluid, and so the fluid's still moving, but that fluid motion is governed by density differences. Okay? And so density differences are the key here, because we know that, depending on the temperature of a fluid, whether it's hot or whether it's cold, its density is going to be different, right? And so if you have a situation that looks like this is kind of the classic situation that we're looking like, where we have a solid surface here, and we'll say that the solid surface has some temperature Ts, right? And if you compare that to the fluid temperature T infinity, let's say that we have Ts that's hotter than T infinity. And so what that's going to do is that's going to heat up the fluid that's right next to the plate, right? And as that fluid gets heated, its density gets less and less, right? And so what you have is that you have basically low density fluid, near the plate, and away from the plate, you have high density fluid because it's at a lower temperature, right? And so because we have these differences in density, we have buoyant forces that's going to drive the fluid to move. Okay. And so it's basically the exact same kind of physics that that makes the hot air balloon rise, right? And so remember, hot air balloon rises because we heat up the fluid on the inside, it becomes less dense, and so it's going to want to travel upwards, right? And so that can also happen kind of on a micro scale here for free convection. And of course, whenever we have any kind of moving fluid, that's going to enhance heat transfer, and that's what gives us free convection, okay? And so, we're this week, we're focused just purely on these situations where we have flow that's driven by density differences. Okay, and anytime you have kind of heat, heat transfer. Remember, heat transfer is always driven by a difference in temperature anyway. And so, whenever you have a difference in temperature, there's always that potential that you're always going to have some kind of free convection because it's always going to, you're always going to heat up the fluid or maybe cool down the fluid. That's going to cause differences in density, and so that's free convection is almost always going to be a factor whenever you have, convection heat transfer, The question is, how effective is it compared to like, forced external convection or forced internal convection? Okay. All right. So any questions so far? So this is kind of just a recap of where we were kind of before the break, since it's kind of been a while since we've looked at this stuff.
And an example would be like those thermal vents out in the oceans.
Yeah, that's definitely a good example. So definitely the ocean, is at a cool temperature. Yeah, and anytime you have some kind of thermal vent or any kind of hot surface, that's a different temperature there. You're going to cause some of the seawater to rise in a column right next to that vent because of that temperature difference. Yeah. Okay. All right, and so specifically, I think where we left off was we were talking about the non-dimensional numbers associated with free convection. Okay. Because when we were looking at external convection and internal convection, we were looking at the Reynolds number, right? And so the Reynolds number was some kind of velocity, so it could either be the mean velocity or the free stream velocity, U infinity, times some length divided by the kinematic viscosity, right? Or this U right here, this was the forced velocity. And then we use this Reynolds number, in a lot of different ways when we were doing external and internal convection, right? So first of all, we use this to determine whether the flow was laminar or turbulent, and we also use this in computing our Nusalt numbers as well. Okay. But in free convection, remember, since we don't have any forced velocity, we don't use the Reynolds number. Right? And so what we use instead is this number called the Grashof number. Right? And so this expression was the following. So we have G times beta times T minus T infinity times L cubed divided by viscosity squared. Okay. Right, and so this is the number that we'll use for these free convection problems. And remember, what this number here represents is a ratio between buoyant forces and viscous forces. Okay. Because remember, whenever you're talking about a non-dimensional number, 9 times out of 10 it's because it represents some ratio of some kind, right? And so remember, for the Reynolds number was a ratio of inertial forces in the fluid okay. And inertial forces are, of course, represented by the force velocity. And on the denominator here, we have viscous forces because we have the viscosity on the bottom. Okay. So whenever you have, a non-dimensional number, 9 times out of 10, it's going to be some kind of ratio. Okay. And with this Grashof number, we're going to use this now to compute our Nusselt numbers, right? Because if you remember from our convection problems before spring break, the way that we computed the convection coefficients was the first thing we always did was compute the Nusselt number, right? But since the Reynolds number here isn't going to be a factor, the way that we're going to compute our Nusselt numbers is going to be some function of the Grashof number instead of the Reynolds number. Okay? It's going to be a function of Grashof number and Prandtl number. Okay. Question? Let's see. Yes. Yeah, and the Grashof number, this is viscosity squared. Yeah, kind of wrote a little bit weird. Mm-hmm. Yep. Okay. And so, I'll show you kind of on the next page, how we actually use this Grashof number. But first thing I want to talk about is, what if you have a situation where you have both free convection and, forced convection, right? And so the question there becomes, what effects is most dominant? Right? because ideally, you know, when you have these situations where, you know, these situations are usually pretty complex. You know, a lot of times when you're performing your engineering analysis, it usually helps you a lot if you can either neglect one quantity or you can assume that one is going to be much more predominant. And so that lets you kind of, you know, it simplifies your analysis quite a bit. Okay. In these situations, what you can do is you can take a ratio, you know, of these dimensionless numbers, right? And so if we take the ratio of the Grashof number divided by the Reynolds number squared, okay? The reason we do Reynolds number squared is because Reynolds number only has one viscosity on the denominator. And so in order basically to cancel that out, we have to do Reynolds number squared, okay? And what this is, so no one has named this yet. And so, you know, if you want to be famous, you can probably name this and write a paper on it. And so this is going to be a ratio of the buoyant forces inside a, you know, a moving fluid versus the inertial forces. Okay. And then from here, we have basically three different situations that we can consider. Okay. And so let's first consider the case where it's very small, and so it's much less than 1. Okay. Right. And so if this quantity here, Grashof over Reynolds number squared, if this is much less than 1, then we know the Reynolds number comparatively is much higher than the Grashof number. Okay. And so in these situations, forced convection will dominate. Forced convection will dominate, and then in these situations we can ignore the free convection. Okay. And so we can basically just treat it as a normal kind of external convection problem or internal convection problem if, you know, if we have this Grashof over Reynolds number squared, if that's much less than 1. Okay. And so this is nice because then we can ignore all the free convection stuff and just analyze it as if it were just forced convection. Okay. And this is generally, you know, when you have cases where you have forced and free convection, generally you're going to be in this realm of, you know, this is much less than 1, just because forced convection just naturally is a lot stronger, just because you have much higher velocities, you know, that you get than just, you know, just from density differences. But, you know, there are situations where it's the opposite, right? And so for a situation where this ratio here is much greater than 1, then what's going to dominate here is going to be free convection. Okay. And in those situations, you can ignore the forced convection and just treat it as just a free convection problem. Okay. And so, you know, this is the opposite situation, but it's still a nice case because here you can just, you know, ignore one thing and just kind of just analyze the other one. Okay. And of course then we have the situation where this quantity is about equal to 1 or in the ballpark of 1. And so in this case, we have, you know, neither forced convection or free convection dominate. And so they're about roughly equal in magnitude. Okay. And so these situations are kind of the worst ones to analyze because, you know, your Nusalt number is going to depend on your Grashof number, it's going to depend on your Reynolds number, and it's going to depend on the Prandtl number. And so, you know, there's not a lot of data out there, or I shouldn't say that. There's not a lot of nice formulas out there that can deal with, you know, a mixed situation like this. And so if you have a mixed situation, probably what you're going to end up having to do is you're going to have to run a pretty expensive simulation in order to determine things like the convection coefficient and, you know, determine convection heat transfer. And so, you know, ideally we just in terms of convenience, we don't like to be in this realm on the bottom here, but sometimes it happens, you know, just kind of based on your design, based on kind of the situation, and you just kind of have to know how to deal with it. Okay. All right. So any questions on this so far? Okay. In our first example, in a bit, I'll show you, you know, how this comes into play and how we can actually compute this. Yeah. Okay. All right, and so that's everything with the Grashof number. But now I'm going to introduce another dimensionless number, you know, which might seem a little bit inconvenient, but it actually makes our calculations nicer. And this is called the Rayleigh number. And so the reason we have the Rayleigh number is that in free convection problems, what ends up happening is that the Grashof number and the Prandtl number often appear together. They even often have the same exponent associated with them too. And so instead of writing, GRPR, for every single problem, this guy Rayleigh kind of became famous in kind of the very easiest of ways. He said, let's just define a new number that's just the product of the Grashof number and the Prandtl number. Okay. And so the Rayleigh number is nothing, nothing too complicated. And so the way that you compute the Rayleigh number is just you take the product of the Grashof number and the Prandtl number. Okay. And so raw is equal to GR times per. That's not a very helpful mnemonic, but if it helps, it helps. So when you see Rayleigh number, and we'll mostly be seeing Rayleigh number from here on out. It's all it is just the product of just the Grashof number and the Prandtl number. Okay. So remember, Prandtl number is something that we usually look up in our property tables. And the Grashof number, we have the formula for that on this page. And so just to kind of simplify the calculations, we just kind of club them together into one. Okay. And so now that we have the Rayleigh number, we're kind of ready to start talking about, our Nusalt number correlations. And in particular, this is going to be for the case that I had drawn on the very first page of this lecture, which is for a vertical plate. All right. And so we have two here. And so we have one for the laminar case and one for the turbulent case. So let's do the laminar case first. Okay. And so for the laminar case, our Nusalt number, which is based on the length of the plate, is going to be equal to 0.59 times our Rayleigh number raised to the 1/4 power. Okay. And that's all it is. So all we have to do here is just compute your Rayleigh number, determine if it's laminar, and then just plug it into this formula. Okay. Luckily, the turbulent formula is equally as convenient. Okay. And so for the turbulent Nusalt number, we have Nusalt number with respect to L is equal to 0.1 times Rayleigh number to the 1/3 power. Right. And so the formula, the formula itself, is not, these formulas are not that complicated. I think the challenge with these convection problems, and you've kind of seen this already with external and internal convection, is kind of just organizing all the data and making sure you choose the right formula. Right? And so most of convection problems are kind of like this, where the formulas themselves are not too complicated. You just have to make sure you choose the right one and you organize all the data and all the parameters in kind of an effective way. Okay. I'll do that on the next page, but the way that we determine whether the flow is laminar or turbulent is a little bit different with this Rayleigh number. Okay. All right. So any questions on this so far? Okay. All right. So how do we determine whether the flow is laminar or turbulent in free convection? And so the way that we determine whether a flow is laminar or turbulent is we, we check to see if the Rayleigh number is above a certain threshold. Okay. Okay. Where that threshold is often called the critical Rayleigh number. Okay. And so the critical Rayleigh number is actually really, really high in this case. The critical Rayleigh number is going to be 10 to the 9th power. Okay. And so if we find a Rayleigh number that's less than 10 to the 9th, then we know that we're laminar. But if our Rayleigh number is greater than 10 to the 9th, then we know that we're turbulent. Okay. And the thing that's unique about free convection is that, if you kind of remember from external convection, we could have like a mixed boundary layer, right? So we could have one section that's laminar and one section that's turbulent. But for free convection, it's kind of an all or nothing thing. So for free convection, if you're below this threshold, then you're all laminar. But if you're above this threshold, then it's turbulent all throughout. And so in that case, it's a little bit simpler than external convection, because you just have to make kind of one decision or the other one, and you don't have to use kind of a mixed boundary layer expression. Okay?
Professor, can you repeat that one more time? You said if it's over, it's laminar.
No, if it's less than this, it's laminar. But if you kind of remember from external convection, you could have a mixed situation where you can have some parts of it are laminar and some parts of it are turbulent. And so that's kind of what you guys did in homework 4. I think for problems 2 and 3, where you had to consider both sections individually. But for free convection, it's not that case. So in free convection, it's either all turbulent or it's all laminar. And so that actually kind of simplifies your calculations a bit. And actually, that reminds you too that, and I think someone pointed out this to me kind of right before the spring break. That integral formula that I gave you for that mixed boundary layer was not correct. And so I think, I don't want to take a break from this right now, just because, we're kind of on a roll here with free convection, but probably at the start of class on Wednesday, we'll talk about that a little bit. And we'll talk about, how you would do problems 2 and 3 on the last homework differently, with the different formulas. So kind of remind me to do that on Wednesday. Okay. Okay. And so now I think we're ready to do an example with all this. All right, and so in this example, let's consider yes, so above 10 to the 9th is turbulent, yes. So it's very high, and so it's actually pretty difficult to get turbulent flow in free convection, okay? Okay, so let's consider a vertical plate that's hotter than a fluid, okay? So this is gonna be hot vertical plate. All right. And so let's say that we have a plate that looks like this. It's vertical, and we'll say that the length of the plate, is 0.25 meters, so it's about a 1/4 meter long. Okay. And the temperature of the plate, we'll say is 70 degrees C. Okay, so it's fairly warm. And then outside the plate, we have fluid temperature, T infinity, of 25 degrees C. Okay. And so in this case, we don't have any forced convection, and so there's no pump, there's no there's no wind that's blowing, and so it's just completely still fluid. But the fact that we have a temperature difference where we have 70 compared to 25, that's going to drive some free convection here. Okay. And we have to know what kind of fluid it is, and the fluid is air. Okay. And so this problem, what we want to do is we want to find the convection coefficient associated with this situation. Okay. And so let's approach this using our convection problem-solving methodology that we've used, for the last few weeks. Okay. All right. So step one. So step one is always to identify the situation. And so basically just describe in a few words, what's the geometry and what kind of convection that we can expect here. Okay. And so in this situation, we have a vertical heated plate in a still fluid. And so the situation is going to be free convection over a vertical heated plate. And so I know that, the first step here is always, a lot of times it's obvious from either the image or, it's obvious from, what week that we're in about, what kind of problem it is. But, I really do think it's really helpful to write this down and kind of really make it explicit. Because then there's no question about, what formulas that you're going to use and how you're going to approach this problem. And so, step one always, might seem trivial. And I think it's the one that's most often skipped. But really, write it down just because it helps you out a lot. All right, step two. So step two, let's compute the film temperature and use that to evaluate the fluid properties. Okay, because remember, whenever you have a fluid, its properties are going to depend very strongly on the temperature. And so it's really important that we compute this film temperature and then evaluate our fluid properties at that temperature. Okay. All right, so I'm going to compute the film temperature on this page, and then I'll write out all the properties on the next page. Okay. But remember, the film temperature is always going to be the average of our surface temperature and our free fluid temperature. Okay. So here our film temperature is going to be Ts plus T infinity divided by 2. Okay. And if we convert that to Kelvin, what we have is about 320.5 Kelvin. Okay. And so now what we can do is we can look up in table 8.4, or you can do what I do nowadays. I just look up an air property calculator on the internet and then use that to to evaluate the fluid properties. Okay. All right. So any questions on this so far? Okay. All right. And so if we evaluate the properties of air at this temperature, okay. Question. You don't have to convert to Kelvin. It's just I think table 8.4 uses Kelvin for its for how you look up its properties, but you can use degrees Celsius as well. Yeah, whatever is kind of more convenient to look up the properties. Okay. And so what we get from that is we get a viscosity of 17.95 times 10 to the minus 6 meters squared per second. We have a Prandtl number of 0.7, and we have a thermal conductivity, Kf, of 27.78 times 10 to the minus 3 watts per meters K. Okay. All right, and so that's everything that we need for this. Okay. But in order to, because we're doing free convection, we also have to compute beta. Okay. Okay. And if you remember what beta was our volumetric thermal expansion coefficient. And so the way that we compute this is actually pretty simple. And so we're just going to take 1 over the film temperature. Okay. Oh, actually, yeah. And actually for this, when you're computing beta, this film temperature has to be in Kelvin. Okay. Okay. And so we do 1 over the film temperature, and this is equal to 3.12 times 10 to the minus 3 Kelvin minus 1. Okay. All right. And so, when you're computing beta, you always need, you do need to make sure that that's in Kelvin. Otherwise, you're going to get kind of the wrong answer here. Okay. Okay. And so now that we have the properties, and now that we have beta as well, we're ready to go ahead and compute the Rayleigh number. And then from the Rayleigh number, we'll be able to determine whether the flow is laminar or turbulent. Okay. All right. So remember, the Rayleigh number is nothing more than just the product of our Grashof number and our Prandtl number. Okay. So it's going to be GR, PR. Okay. PR we know from the tables, right? And so we know that PR in this case is 0.7. But the Grashof number here, we do have to compute. And so our Grashof number, our formula for that is going to be beta, gravity, G times beta, times the temperature difference between the surface and the fluid. We multiply by L cubed, and we divide by the viscosity squared. Okay. Multiplied by Prandtl. Okay. And so in this case, we have all these quantities because we can plug in for gravity. We can plug in for beta. We know the temperature difference. We know the length. We know the viscosity. And of course, we know the Prandtl number. Okay. And so what we get for the Rayleigh number is 6.67 times 10 to the 7th. Okay, for this case. And since this Rayleigh number is less than 10 to the 9th, then we know that this is a laminar situation. Okay. All right. Any questions on this so far? Okay. All right. And so now that we have the Rayleigh number, we can go ahead and compute the Nusalt number. Right, so step 4 is always going to be select the correct Nusalt number correlation. Okay, select the appropriate Nusalt number correlation and compute the Nusalt number. And so since we have a laminar case, then our Nusalt number correlation is going to be 0.59 times the Rayleigh number to the 1/4 power. Okay. We just computed Rayleigh number from the previous page. 0.59, we know exactly what that is, right? And so what we get is a Nusalt number of 53.32. Okay. Right. And now that we have the Nusalt number, what we can do is we can use this to compute our convection coefficient. And so since we know that the Nusalt number is also equal to the convection coefficient times our length divided by kf, okay? What this tells us is that h is equal to kf over L times our Nusalt number. And then we plug everything in here, and what we get is a convection coefficient of 5.925 watts per meter square. And this is 5.925. Okay. And that's the end of this problem, because this problem, we're only looking for the convection coefficient. And so we have done that. So now we're done here. Okay. All right. So any questions on how we did this example here? Okay. So, you know, the process of doing these free convection problems is the same as we always have. The only thing is that you're just using different, you know, you're computing the Rayleigh number instead of the Reynolds number, and you're using different Nusalt number correlations. But besides that, you know, the process is, you know, exactly the same as what you did for homework 4. Okay. Okay. And so that's it for this problem. But one thing that I've kind of added to this example is what happens if we took the same situation and we put a fan underneath the plate. Okay. Okay. And so, you know, this is our original situation. Okay. But what happens if we took a fan and this was kind of rotating and this was kind of forcing air to flow above the plate? Okay. And so now we have a situation where we have forced convection in addition to free convection. Okay. Right. And so, you know, whenever we have the situation where we have both, you know, forced and free convection, you know, what we're interested in is, you know, which one of these is going to dominate. Okay? And so let's say for this case that the fan will blow air at a speed of 5 meters per second. Okay, so that's going to be U infinity. Okay. And so from here we can compute the Reynolds number, because the Reynolds number is going to be U infinity times L divided by nu. Okay. And so this gives us 6.97 times 10 to the 4th. Okay. Right. And so that's based on our on the velocity that we're forcing. Okay. And so now what we can do is we can compare this magnitude to the Grashof number and see whether the flow is going to be either buoyancy dominated, or it's going to be inertia dominated, or it's going to be neither, and we have just a big mess on our hands. Okay. All right. So any questions on this so far? Okay. All right. And so now that we have the Reynolds number, we can go ahead and compute the relative magnitudes of the Grashof and the Reynolds number. All right. And the reason we're doing this is we want to see whether the flow or whether our convection is going to be either forced dominated or free dominated. Okay. And so what we can do is we can take the Grashof number and divide by Reynolds number squared. Okay. And we have all these things for this problem. And so we have the Grashof number, which we computed, as part of the example earlier, and we just computed the Reynolds number. And what we get is 0.014. Okay. And since this is much, much less than 1, right? And so it's basically only 1.4% of 1, then we know that this flow is going to be inertia dominated. Okay. And so oh, yep, what's up?
So you said like if it's like much less than 1, what if it's like 0.7?
Yeah, no, it's a good question, and so so the question is, what's the threshold for being much less than 1 or not? And so I would say, for me, if it's less than 0.1, and so basically what you're saying is there is like the inertia is basically 10 times stronger than the buoyancy. That's usually a good threshold for that. And for the other direction too. So if this ratio was over 10, and so I think that's usually enough for you to say that the free convection dominates. So if you go, 1 order of magnitude, so you either go, either 0.1 or 10. Once you're past that, then then you can assume that 1 is basically negligible. Yeah.
Okay.
Okay. And so since, in this case, since we got 0.014, in this case, we can ignore free convection. Okay. And so probably if we analyze this with, with our external convection, and so we used, our Nusalt number correlations for those, probably what we'll see is that we'll see a convection coefficient that's above 100 or something like that. Okay. And so if you compare that to the convection coefficient that we got just now, which was only 5.9, you can see that, that's much higher. Okay. Okay. So this is basically how you would perform that comparison in between the two. And so, this is always helpful to do because, you usually don't want to get yourself in a situation where you have to do both free convection and forced convection, because usually they're not separate. So usually they're going to interact with each other, and it's going to make your life a lot more difficult. And so, when you're doing kind of practical problems, if you do calculations like this and you can kind of, simplify your life a little bit, that usually is going to help you out a ton. Okay. And so, we're doing this here, strictly for just free convection, but this is kind of a good skill to know in general. Because a lot of times, even though, real situations like you're talking about, designing like an airplane or something like that, there's literally a million different things that are going on at the same time. And so if you can make your life simpler and cross off, a few dozen things, that's going to make your analysis a lot easier. And it's not a question of making it easier or not because you're lazy or something like that. A lot of times it's a question of time, right? So a lot of times you're doing engineering analysis and you have deadlines that you need to meet, right? And so if you can do a faster calculation and still get accurate and reliable results, that's always going to be a good thing, because that means you meet your deadlines faster. That means you're going to be more efficient as a worker, and you're just going to get more work done. Okay, and so. It's not a laziness thing, and so don't make people think that it's like that at all. It's just a time thing. Okay. All right. So any questions on this? Okay. All right. So the next thing I want to go over is I want to talk a little bit more about the forces that drive the Grashof number and the Reynolds number. And so this is kind of like a little bit of a conceptual detour, because I want to kind of focus on two specific quantities in these formulas that really tell you, what's really, driving the force behind all of these, right? So let me write down both formulas here. And so let's start with the Grashof number, okay? And so the Grashof number is gravity times beta times T minus T infinity times L cubed, okay, divided by viscosity squared, right? And the Reynolds number here is going to be U infinity times L divided by viscosity here, okay? Okay, and so in particular, we have these two formulas here, and we've kind of seen that they're kind of analogous to each other in certain situations, okay? And in particular, I want to focus on these quantities that I'm going to box here, okay? Because these are really kind of the driving forces, behind what drives these quantities to be either really, really high or really, really low, okay? And in particular, these are the ones that we usually have the most control over, okay? So the box quantities, these drive the magnitudes of these numbers. And as engineers or as designers, these are usually the quantities that we have more control over. Okay? Relatively speaking. Right. It's like, you can't really control what gravity is. You can't really control the viscosity of the fluid you can to a certain extent, based on the temperature, but, not that strongly. The length, of course, the length that you have control over that, usually when you're designing something, but sometimes you're constrained by other things. But, when you're talking about what are the things that are driving these numbers, it's really the quantities that I have boxed there. Okay. All right. And so for the Grashof number, what we can say based on what I've boxed there is that free convection is driven by temperature differences. Okay. And so what that tells us is that the higher the temperature difference is between the surface and the fluid, the more convection is going to occur. Okay. Whereas for forced convection is really just determined and driven by the velocity. Okay. Okay. And so the higher that velocity, the higher the Reynolds number is going to be, and it's going to give us more, more convection. Okay. And so what does this mean in terms of turbulence, right? And so we know that, for both the Grashof number, or I guess technically the Rayleigh number, and the Reynolds number, if once these pass a certain threshold, then we have a turbulent flow. Okay. And so we've already seen that, for forced convection, if you have very high velocities, generally that's going to lead to turbulent flow. Okay. But for free convection, the mindset is kind of flipped a little bit. And so because free convection is driven by this temperature difference, if you have very high temperature differences, then that's what's going to turn your flow turbulent. And we'll do an example next of a turbulent case. I think our first example today was laminar, And so, you know, we'll do a turbulent case just so you can kind of see what that looks like. Okay. All right. So any questions on this? Okay. So let's, so the last example that we did was kind of a, you know, it was kind of a generic plate and a generic fluid. You know, it was, you know, kind of a little bit disconnected from reality. And so for this example, I want to do something that hits a little closer to home, literally. And so let's consider, you know, free convection from a fireplace. Maybe not so common in California because, you know, I don't know about you guys, but usually it doesn't get cold enough for me to turn on the fireplace. Really only if you're roasting marshmallows or something like that. But let's assume that, you know, we have a fireplace inside our home. And in particular, let's consider a case where we have the fire that's kind of covered partially by a glass door. Okay. Right, and so now we can reap the benefits of doing a multicolor because now I can draw this fire in red. Looks like just a fern, but you know, it's fire. Okay. And then we can say that this fire is going to be covered by a glass door that looks like this. Okay. And then let's assume that the temperature of the glass door, because it's, you know, right up on the fire, let's assume that the temperature is going to be 232 degrees C. Okay. Right. So we also know some dimensions about this glass door. So let's say that the length, you know, going up and down is going to be 0.71 meters. And then the width of the glass door going into the page, that's going to be 1.02 meters. Okay. And then outside this this glass door, you know, you have a living room. Okay. And so the living room is filled with air. Okay. And so, you know, we're not doing some SpongeBob SquarePants weird thing. And so, you know, these are humans on land. Okay. Right, and so let's say that the temperature of the room is kind of a nice, comfortable 23 degrees C. Okay. All right, and so what we want to solve for in this problem is we want to find the rate of convection heat transfer from the fire to the room.
Sorry, is the width like the into the page like distance?
Yes, yeah, so the width is going into the page, yeah. Mm-hmm. All right. And so here, you know, we have a situation where we have a pretty extreme temperature difference. So on one hand, you know, we have a temperature that's over 200 degrees C, and in the living room, we have kind of regular ambient air quantities. And so this is a situation where, you know, we're more likely to be turbulent because we have this huge temperature difference, okay? And we're going to assume that there's no external flow at all too. Okay. And so that's our situation. And so let's go ahead and use our convection problem solving methodology that we've always used, okay? And so first step is always going to be identify the situation. And so the situation is the same as the last one. And so we have a vertical heated plate, free convection. Okay. And so next we're going to evaluate the film temperature and compute the fluid properties. Okay. And so our film temperature here is just going to be the average between the two. Okay. And so the average is going to be Ts plus T infinity divided by 2. Okay. And we plug those guys in, and what we get is a film temperature of 400.5 Kelvin. Okay. And I'm converting to Kelvin here because we're going to need it to compute beta as well. Okay. All right. And so on the next page, I'll write down what I got for the properties. But before I do that, are there any questions on this? Okay. Okay. And so now that we have the film temperature, we can go ahead and look up the properties. And so this is what I got. Okay. And so for the thermal conductivity, we have 33.8 times 10 to the minus 3 watts per meter K. Okay. We have the viscosity. So the viscosity is 26.4 times 10 to the minus 6 meters squared per second. We have the, in this case, the thermal diffusivity as well. Okay. And so this is 38.3 times 10 to the minus 6 meters squared per second. We have our Prandtl number, which I think in this case we had to do by taking the ratio of the thermal diffusivity and the viscosity. Okay. And then what we get from this, or maybe it's the other way around, is 0.69. And of course, we have a beta, where beta is just going to be 1 over the film temperature. Okay, the film temperature being 400. And what we get for this is 0.0025 Kelvin to the minus 1 power. Okay. All right, and so that's all the properties that we need for this problem, and we can go ahead and start computing things. All right. Okay. And so since we're doing a free convection problem, normally at this point we compute the Reynolds number, but since we're doing free convection, we're going to compute the Rayleigh number instead. Okay. And so the Rayleigh number is the product number as the product of the Grashof number and the Prandtl number. And so it's G times beta times Ts minus T infinity times L cubed divided by viscosity squared times the Prandtl number. Okay. In this case, what we get is 1.813 times 10 to the 9th. Okay. And since this number here is greater than 10 to the 9th, this means that we have turbulent flow. Okay. And so that's going to affect which Nusalt number correlation that we end up choosing. Okay. And so now that we have the Rayleigh number, we're ready for step 4. And step 4 is selecting the appropriate Nusalt correlation and then computing the Nusalt number. Okay. Okay. And since we have turbulent flow here, our Nusalt number correlation is going to be 0.1 times the Rayleigh number to the 1/3 power. Okay. So we can go ahead and plug those in, and what we get is 121.8 936. Okay. And then now we can use this Nusalt number to compute H. Okay. All right. Any questions on this so far? Okay. All right. So step 5, use Nusalt to compute H. Okay. Right, because we know that the Nusalt number is going to be equal to H times L divided by KF. Okay. We plug in for the Nusalt number, which we just solved for. We plug in for L, we plug in for KF. And what we get is an H of 5.8 watts per meter squared K. Okay. Okay. And so now that we know H, we are now ready to compute convection heat transfer. Okay. Okay. Because now that we have H, we can just use our Newton's law of cooling that we always use for convection heat transfer, right? And so Q is going to be equal to H times A times the temperature difference. Okay. And so in this case, we have everything here because we have H. We just solved for it up there. We can compute the area, and so the area is going to be the length times the width, and of course we have our temperature difference. Okay. And so we plug everything in, and we get 877.88 watts. Right. All right, and so that's that's an example with turbulent flow, and so you can see it doesn't make that big a difference here because for free convection it's either all laminar or all turbulent, and so the only thing that changes is the Nusalt number correlation that we compute on step 4. Okay, but besides that, this whole convection problem solving process is all the same. All right, any questions on this example here? Okay. All right, and so up to this point, we've just been working on just vertical plates, and in particular, both examples were kind of the same, where we had a hot vertical plate relative to the fluid, right? Okay. And as we know that when we heat up a fluid, it generally gets less and less dense, and so when you have a hot vertical plate in a fluid like this, right, what's going to happen there is that the fluid next to it is going to rise, right? And so you have fluid flow patterns that generally look like this. Okay. But you can have free convection in the opposite situation too. So if you have a cold vertical plate, meaning that your surface is colder than the immersed fluid, right? Then you're going to have the fluid next to it kind of get more dense. Okay, and when a fluid gets more dense compared to the fluid around it, by buoyancy forces, that's going to cause the fluid to fall. Okay. Okay. And so let me write out. So for the hot vertical plate, we have Ts is greater than T infinity. Okay. For the cold one, we have Ts is less than T infinity. Okay. Right. And so we get different flow patterns for each cases. And so the question now becomes, does this have an effect on our calculations, or is this going to affect our Nusalt number correlations? Okay. And so if we kind of did the reverse of our two examples, and so if we did the previous two examples where the surface was colder, is that going to change your answer? Okay. Okay. And thankfully, the answer for this is no. And so if you have a vertical plate, it doesn't matter if the vertical plate is cold or hot, you're going to do the same calculations anyway. Okay. Okay. And so that's kind of nice. And so, when you're considering vertical plates, it doesn't matter which one's hotter or colder, you're going to get the same thing. Okay. All right. But what about horizontal plates? And so horizontal plates are kind of, the opposite. Instead of, the fluid kind of flowing around that, for a horizontal plate, you're going to have either fluid that goes away from your plate or towards it. Okay? And so for horizontal plate, it makes a difference. And so the main reason is, it can, depending on, the temperatures, it's either going to drive fluid towards the plate or away from the plate. Because whenever you have kind of buoyancy driven flow, it's always going to go vertically up and down because it has to follow the gravity field. And so when you have a plate that's horizontal, you can either have flow that goes vertically up away from the plate or vertically down towards the plate, and the opposite too. And so if you have fluid underneath the plate, it's either going to go vertically up towards it or vertically down away from it. Okay. And so whether you have fluid coming towards or away from it, it makes a difference. Okay. All right, and so any questions on this so far? Okay, and so let's first consider a case where we have a hot horizontal plate. And so our horizontal plate in this case is going to be hotter than the fluid. Okay, and so we have a situation that looks like this. Okay, and so remember, because the plate is going to be heated, the fluid around it is going to become less dense. Okay, and so what you have is kind of these two kind of flow patterns, right? And so if you have fluid that's on top of a hot plate, then what it's going to do is it's going to drive fluid away from the plate. Okay, and so you're going to have flow patterns that kind of look like this. Okay. So you have fluid that kind of comes in, it gets next to the plate, then as the plate heats it up, it's going to drive it away. Okay. All right, so ultimately, you're going to have flow away from your hot plate. Okay. But if you have a hot plate on top of some cooler fluid, what that's going to do is going to draw fluid towards the plate. Okay, and so you're going to have flow patterns that look like this. And so you're going to have fluid that comes up, It's going to hit the plate and it's going to go around. Okay. And all these situations here, you have, fluid going vertically up. Okay. All right. And so just to kind of summarize this in words. Okay. Okay, so for a hot plate, okay, fluid on top of the hot plate will move away. Okay. Okay. Whereas fluid on the bottom will move towards the plate. Okay. And depending on the, depending on the direction of the flow, whether it's going towards the plate or away from the plate, that's going to change our Nusalt number correlations. Okay. So any questions on this before we go over a cold plate? Okay. All right, and so let's do a cold plate now. So the cold plate is going to be basically just kind of the opposite of the situation. And so for a cold plate, let's say that, we have this plate here and it's relatively cold. Okay. A cold plate is going to make the fluid become more dense. And so you're going to have fluid that comes towards the plate from up top. Whereas on the bottom here, you're going to have fluid that kind of turns away. Right. And so on the bottom here, for a cold plate, fluid on top is going to go towards the plate. Whereas fluid on the bottom will go away from the plate. Okay. All right. And so what we'll see on Wednesday is, depending on whether the fluid is going towards the plate or away from the plate, that's going to change our Nusalt number correlations. Okay. Okay. And so on Wednesday, we'll look at, what those correlations are. You'll see that they're, relatively simple. It's just, the hard part is picking the right one. And then we'll do an example where you can kind of see this in action. Okay. All right. Any final questions before we wrap up for today? Okay. All right, so that's all we got time for today. So thank you guys for tuning in. And so remember, homework 5 is posted. And so remember, you definitely start working on that because it's due on Monday. Okay. If you have any questions on that, definitely let me know. But thanks for coming today, guys. Have a good rest of your afternoon, and I'll see you guys on Wednesday.
Thank you, Professor.
Thanks,
Thanks,
guys.
guys. Have a good one.
Thanks, guys. You too.
Professor. Well, Professor, one question for you.
Sure.
That's fine.
Mhm.
So then is that how like those the currents form in the ocean?
Yeah, so it's yeah, currents in the ocean are definitely a pretty complicated thing in reality. But temperature and density differences play a big role. It's even bigger. It's even more enhanced in the ocean because you have salt content is something that's really important as well. And so depending on how much salt content is in a certain patch of fluid, that's gonna cause density differences as well. And so that's kind of another layer on top of this. And so definitely density differences play a big role in the ocean.
Okay, thank you.
Mm-hmm.
Have a nice day.
Thanks, you too. All right. Jorge, did you have any other questions? Okay. All right. So I'm gonna go ahead and close the call. Have a good day. I'll see you on Wednesday.